Okay, so happy Monday. We are moving on to the next portion of our trig functions as far as graphing them. Okay, so I'm going to go ahead and let you work on your bell ringer. I want you to pause the video, take no more than 10 minutes to answer this, and then make sure that you unpause the video and go on to the next part of graphing, because we're now actually doing transformations on our sine and cosine. Okay, so again, pause the video for no more than 10 minutes and answer this, and then I'll come back and I'll do it. Okay, so you should have paused the video. The transformations that have occurred to the vector for -7 to make it become -8, 14. Okay, the way we phrase these is we dilated by 2 and we reflected. Right, because the positive became negative, the negative became positive, that's the reflection, and everything has been multiplied by 2. So it's been made twice as long, and it's been reflected from going over here to over here. Okay, so it has been reflected. If you want to be specific, it's been reflected across the origin or across the line y equals x. Okay, so since both the x and the y got reflected. All right, so the center and the type of shape that this is. Well, your clue to the type of shape should be the minus. This is a hyperbola. Okay, and don't let it fool you just because the y is going first. The center still starts with the x and they both change sign. So the center is -3, 4. And that's something that caused a lot of you problems on the last test, on the conics test. You would get your center backwards, which means you'd get your vertices and foci and everything else backwards. So good practice. All right, on to what we are working on today, and that is transformations of sine functions. Okay, what we graphed on Friday was y equals sine of x and y equals cosine of x. Okay, this is the way that these are actually written when we have all the different pieces that we can do to them. Okay, it's not a lot. It's just there's 4 different things that you can do to this type of function. It's very similar to even quadratics and everything else that you graphed back in Algebra 2. The biggest difference is going to be this, the number in front of, or the letter in front of the x. That's a different type of transformation than we've seen in quadratics, and that actually changes how fast the graph cycles. I talked a little bit about that on Thursday and Friday about how you can make, like in music, if you turn the frequency up, you can make the graph bounce faster, right? It's not going to take 2 pi to go through one full curve. It'll do it faster. That variable changes that. Okay, so there are 4 different ways that these can be changed. Today we're going to concentrate on A and D. Okay, so we'll define them for you just to make sure you have them all. A is your amplitude. Okay, that's basically how far your graph stretches, how far it goes up and down. Amplitude means that we can dilate it, make it smaller or bigger, and we can also reflect it. We can flip the whole function over. Okay, so amplitude works just like A in a quadratic or A in any other function that you've dealt with all the way back to freshman year. All right, B takes care of your cycle, or what we call your period, as in how far it takes for one full curve. Okay, and believe it or not, you can actually figure out for B pretty easily, because B tells you how many times the graph is going to cycle in one 2 pi graph. Okay, so it's basically how much for one full curve. All right, C, it's different phrasing for this. You know this as a horizontal shift. Okay. And it's the exact same thing that, again, that horizontal shifts have always been, it's where left or right did I move the graph. Well, in our case, a horizontal shift is where does the graph start? Because normally the graph starts at 0, right? And if we move the graph left or right, then it's not going to start at 0 anymore. We need to figure out where. Okay, so C is what allows us to find our phase shift. All right, and then D is how we find our vertical shift, right? And that would be, again, where does the graph start? And obviously if it's vertical, then we're talking about up or down, right? That's up and down. And if that's a phase shift or horizontal, that's left and right. So we can take that, like for instance, the sine function that starts at 0, 0, and we could move it over to the right and up, and we could make the graph start in a different spot. Okay? And again, that's really helpful when you're talking about doing these for real life stuff, like waves and temperature and sound and all that kind of stuff. Okay? So again, today we are going to be sticking with amplitude. How far can I stretch it or make it smaller? And vertical shift, how far up or down can I move it? Okay? So that's everything that we're going to be dealing with today. And then for the rest of the week, we're going to be dealing with how to change the cycle, how to change the phase shift, and even going as far as to write the equations, given some information. Okay, so let's do a basic. Okay, so this is your basic. We're just going to put a number basically in front of the word sine. And don't worry about that symbol, that's theta. You can see theta, or you can write it as x, or you can write it as alpha, or anything else. It's just a variable, and normally we say theta if we're talking about an angle. So not a big deal. You use whatever symbols you like. All right, so, okay, go. All right, so we've got a sine of x, and a is an amplitude. The big thing about this is even when the number in front of your sine x is negative, your amplitude is always read as a positive. We did the same thing, again, back in Algebra 2. That a dilation is separate from a reflection, right? If the number in front of your function gets bigger, even if it's a negative and it's bigger, that's still a dilation, and the reflection is a separate type of transformation. It's the same thing here. So your amplitude is always considered positive, even if I were to write a negative number in front of it. Okay, that just means it's also been reflected. So for this one, this is our normal sine function. Okay, and I could continue this down here, right? This is what we normally look at. And this is just going, imagine if you were doing your counterclockwise, or your clockwise for your negative angles. This would be negative pi over 2, and this would be negative pi, right? And then this would be positive pi over 2, positive pi, positive 3 pi over 2, positive 2 pi. Okay, that's our normal function. And it can be, put in the back as far as negatives. It can be put forward as far as positives. You can go backwards around the unit circle. Okay, so notice that it has an amplitude of 1, right? It goes from -1 to +1, which, by the way, is also the range. If I wanted to know the range of my normal sine function, it goes from -1 to 1. Okay, so let's see what else I have in store. All right, so let's just say, for instance, because I can, aha, there it is. Okay, so let's see, and, there it is. Okay, and I'll trace it in red just to make sure you can see it. No, I said red. There we go. Oh, messy. And I can keep going on this one too. Okay, so that function, if you compare it to the original sine function, has been changed. It's been dilated. Okay, so where does it appear to be starting and stopping as far as how high up and down on the y that it goes? If you said a half, you're correct. So we would write that function as y equals 1/2 sine of x. We've changed how high up and down this goes. Well, that means we've also changed the range, because the range is all your y values. That means we've only gone from -1/2 to +1/2. Okay, it kind of shrinks the function down. All right, let's try one on cosine. All right, so again, take a look and go ahead and mark this as +1 and -1. Okay, and see that's our normal function. So we would just call that y equals cosine of x, which is the same exact thing that we graphed on Friday. All right, so if I go ahead and apply a dilation to this one, okay, got it in there. Oh, nope, not that one. There we go. All right, so let's take a look. Do that one in purple. And notice it's the same exact function. It still, has, at 0 is its high point, right? Okay, we've just shrunk it. Okay, this looks like it's definitely less than half, though, this time, right? Because, half would be about right here. So I would say this is either a third or a fourth. Okay, your choice, either a third or a fourth, and you would write it as either 1/3 cosine x or 1/4 cosine x. And, if in case you're wondering, yes, the graphs that you will be writing equations from will be very, very specific as far as where the points are. You will be able to tell if it's a third or a fourth. It will be very, very obvious as far as the markings on the graphs. For today, what you're going to be doing is you're going to be graphing these equations and stating what the amplitude and what the vertical shift and what the range is. So for these, again, if I'm going to go a third, then my range is from -1/3 to +1/3. And for here, it would be from -1/4 to +1/4. Okay, so that's how we change amplitude. So let's talk about how we change vertical shift, which there's another name for a vertical shift, and the other name that you'll see is called a midline. And they call it the midline because it's literally like an imaginary line that goes through the middle of the graph. Right now, this is, again, my normal sine function, and its midline would be 0, right? It hasn't been moved up or down. It starts at 0, it comes back to 0, so 0 is its midline, okay, the middle of the graph, like if we were to cut the line through it. Okay, so let's apply a transformation and make it move up or down. Okay, so we've got the regular graph, y equals sine of x, and in the blue, y equals sine of x plus 2. Okay, very, very easy. We take the entire graph, entire normal function, and we move it up 2. Okay, so what would that look like? Blue. It would look like that. You took every point, and especially the 5 that we usually use to graph from, you took every point and you moved it up 2 spots. This goes from 0 to 2, this one went from 1 to 3, 0 to 2, -1 to +1, 0 to 2. All you did was move the entire graph up. Okay, so let's try one with cosine. Okay, and there's my normal cosine function, y equals cosine of x. Okay, that starts at 1, goes down to 0, then -1, and then back up to 1, right? Notice again, though, that 0 is still its midline. It would cut the graph in half vertically, right, as far as half being above it and half being below it. Okay, so my transformation on this one is to take that entire graph and shift it down 3, -3. So we're going to move the whole graph down 3. So every point goes down 3. So that goes from 1 to positive, or -2, rather. And this one goes from 0 to -3. And this one goes from -1 to -4. And from, again, 0 to -3. And from 1 down to -2. So my new function is right there. The entire graph has been shifted down 3 points. Okay? And that's what you're going to be talking about today. Now, we didn't write it. I need to go back up and do that. What would be the new range of this sine function that's been moved this way? Well, before it was from -1 to 1. Well, this new function bounces between, as far as the low and the high, +1 to +3. And we know that because we went from, if you think about it, -1 to 1, we added 2 to both of those because of the vertical shift. Okay? Better to graph them to be able to pick out your range, though, because what happens, and we will be doing this, if you apply an amplitude change and a vertical shift. Okay? So better to graph it, that way you can see where it's supposed to go. All right, what about the new range on this one, as far as from the lowest to the highest? All right, well, this one goes from -4 to +2. 4 to +2. There we go. All right, so let's go ahead and practice some where we're doing both, where we're actually doing a vertical shift and an amplitude change. All right, we're going to do these together, and then I'm going to give you your assignment. Okay, so let's draw some basic lines because, you know, that's how we graph this. Okay. And I can kind of cheat as far as depending on my graph. If I know where the graph is going, I don't have to make my line so big, right? I know if I am multiplying my whole sine function by 4, that means instead of going up to 1 and down to -1, it's going to go up to 4 and down to -4. And I haven't changed anything else, so I can just kind of do this. I don't have to make my graph so huge, right? And I can get it to still fit. Now, please note that the points that the graph changes at 0, pi over 2, pi, 3 pi over 2, and 2 pi have not changed. We'll talk about that starting tomorrow as far as changing what those points are, okay? But for right now, they're going to stay the same. We have those 5 points, right? That's from 0 to 2 pi, 1 trip around the circle. And remember how we split those into equal parts, right? What's halfway between 0 and 2 pi is 1 pi. And halfway between 0 and pi, so we cut each of those in half again. Okay? So very important that it still starts and stops in the same place for now. So this one, again, just has an amplitude change of 4. So I'm still starting at 0. And I'm going up to 4, down to 0, down to -4, and then back up to 0. So for those of you who made that mistake in your graphing your basic sine and cosine, a sine function, doing this, the normal sine function, increases, decreases, decreases again, and then increases again. So it's up, down, down, up. Okay, and that is our graph as far as what this should look like. Our amplitude is 4. Our midline is still, not x, excuse me, that should be y equals 0. Our midline should still be y equals 0 because it's still starting, you know, the middle point is still at 0. And our range goes from -4 to 4. And this is what I'm going to expect you to do today. All right, let's try the next one. Okay, so what has been done? What transformation has occurred? This has been reflected, okay, just like this one was dilated. Okay, if it's been reflected, that's something very interesting as far as with a sine function, okay? It literally flips everything over the x-axis, okay, but that doesn't affect where it starts because 0 is not a positive or negative, so that can't change as far as flipping over anywhere. What can change is basically it makes a reverse pattern. It's actually pretty neat. It starts at 0, and instead of going up to 1, it's basically we're going backwards around the circle. It goes down, and then back up, and then back down. Excuse me. So imagine if you put a negative in the front of a sine or cosine, it's like you're going backwards around the unit circle, because this would technically be, negative pi over 2 would be negative 1 for your y value. Okay, so, and the graph just gets flipped over, just like that. All right, now here's the test. Your amplitude is still 1. Okay, that negative has nothing to do with how much that graph has been stretched. What's your midline? Still y equals 0. Good, we haven't moved it. And my range hasn't changed at all either. It's still from negative 1 to 1. Right? It's still lowest to highest. Doesn't matter where it's at. So that one has been reflected. It's been flipped over. All right, let's try one that's a combination of both. So we've got y equals 2 sine x minus 1. Okay, so it's been stretched by 2, right? And then 1 has been subtracted from it. Okay, and sort of like solving an equation as far as what you do first. Okay, so, all right, that's 2, negative 1, or 2, 1, 0, negative 1, negative 2. I'm still going to have pi over 2 and pi and 3 pi over 2. And really, you need to label your graphs just like this every time. Okay, so in order, as far as what's been done to the function, you first multiplied it by 2, actually, and then subtracted 1. Okay, so order of operations. So if I first multiply by 2 and then subtract 1. So let's put up my normal graph just so you can see how this works. There we go. Okay, so this is the normal sine function from negative 1 to 1, right? Okay, so each piece gets multiplied by 2 and then you subtract 1. So let's see what that would look like. So 0 times 2 is 0 minus 1. No problem. Okay, remember it's just the y values I'm talking about. The y value is 1, times 2 is 2, subtract 1 is 1. Okay, again, 0 times 2 is 0, minus 1 is negative 1. Okay, this one's at negative 1. Negative 1 times 2 is negative 2, minus 1 is negative 3. Okay, and then the next one, 0 times 2 is 0, minus 1 is negative 1. Okay, so let's take a look at it. So hopefully everybody can see. And again, all I'm doing is taking the y values and doing this in order. Okay, so times 2, then subtract 1. Okay, and it's on your y values. Okay, so take a look at the original function in blue and the new function in red. You can tell the graph has been stretched, right? Because it's now going from negative 3 to positive 1. So that's twice as wide as it was before. And then you've also moved the entire graph down 1. Okay, so if all I did was move it down 1, it would start at negative 1 and go to 0 and go back to negative 1 and go to negative 2 and then back up to 0, right? If that's all I did to my original function was just move it down 1, that's what it would look like. Okay, so I had to stretch it by 2 and then subtract 1. If all I did was stretch it by 2, this would be what the function would look like. It would still be sitting at 0, and it would be twice as tall in either direction. Okay, so we're combining both. And you need to do them in the order that they're given. Okay, so my amplitude is 2. My midline, well, my midline is no longer y equals 0 because it's actually been shifted down. My midline is y equals -1. Okay, and my range, well, the lowest is -4 and the highest is 1. So -4 to 1. Okay. Let's see. I'll tell you what. We'll throw the negative in front of the 5th one and do this all at one time, because I know y'all can do it. Okay, so, and again, we have to think about what transformations have occurred and in what order, because it makes a difference. All right, so here's my graph, and pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so this is going to take my y values, right? It's just my y values, and it's going to multiply by -2 and then add 3. Okay, so first you're going to take all your normal y values, you're going to multiply them by -2, and then you're going to add 3. Okay, so this is a cosine one, right? So normally cosine starts at 1, right? Okay, I'll draw the normal one just so you have the reference, and it's a good idea for you until you get used to what the new graph should look like. Okay, so you can see all your y values, it kind of helps. All right, so let's see what we got. We're going to take each one of our whole number points, and we're going to multiply them by -2 and then add 3. All right, so 1, all right, so 1 times -2 and then add 3. So that's -2 plus 3, that's going to be at 1, doesn't change, right? So multiply by -2, then add 3. No, that you're still back at 1. Okay, that's fine, we're good. All right, take the next one, that's 0, right? 0 times -2 plus 3, that's going to be 3. Okay, so that's where that's going to be. All right, take the next one. The next one would be -1, right? So -1 times -2 plus 3, that's going to be 5. Oops, I'm going to be all the way up here. Okay, and since it's symmetric, if I do 0 again, I should get 3, right? And if I do 1 again, I should still get 1. So my graph did several things here. Okay, and we would be able to tell based on the graph what's been done. Okay, first off, we know it's been reflected because it's facing downward instead of facing up, right? Secondly, it's only supposed to go down 2 and then back up 2, right? The original, well, this is going up 4 and back down 4, so it's definitely been dilated by 2. Okay. Now here's the thing, how do we know for a fact that it has been moved up 3? Okay, well this is the hard part to get you to understand, okay? If all I did was reflect my cosine, okay? If that's all I did to it, instead of starting at 1, it would start at -1. And this is what it would look like, okay? Stay. Uh-oh, hopefully I didn't mess that up. Yeah, okay. So it would start at -1, right? So we need to understand that, actually that's only been moved up 2. Why has it only moved up 2? Let's make sure that we did that right. Okay, so multiply by 2 to make it -2 plus 3. Nope, that's right. Okay, so then we would know that it's been moved up, although I would have said this has only been moved up. Hang on, if I reflect it, 1, and then move it up 1. Yeah, that would only be 2. Weird. I'm going to have to check on that one. All right, for right now, have to figure out why that's only been moved up 2. Have to get my graphing calculator out and type that in and find out what's going on. Okay, so based on the equation, reflected dilated by 2, and it's been moved up 3. And those points are all correct because we did the right order. We multiplied everything by -2 and then added 3. We're doing good. Okay, so our amplitude is 2. Our midline, well, what is the actual halfway point between 1 and 5? 3. So your midline is y equals 3. And your range, again, just lowest to highest, 1 to 5. Okay, so I've got 4 problems for you to do in Canvas. They're on a worksheet. The worksheet is called Transformations 1. Okay, the graphs are already on there, the equations are already on there, but I do want you to state amplitude, midline, and range. All right, take it easy. You should be having another video lesson tomorrow, and then I'll be back with you on Wednesday, but you feel free, send me questions if you need to.